This is Relatively Prime 2019 in the mathematical domain. I am Samuel Hansen. Hello, Relatively Prime listeners. We are at the end of 2019, and this year I wanted to do a little bit of a wrap-up of what has happened in the world of mathematics this year. And to help me do that, I am joined by Katie Steckles and Christian Lawson-Perfect from the Aperiodical. Hello, y'all.
Hello.
Hi.
And so was there anything to either of you that has sort of stuck out from the year 2019 when it comes to mathematics?
Well, I guess for me, a really recent thing that's happened. I can't remember anything that happened prior to this because I've just had Christmas and eaten everything. So I can't remember anything from before this week. But the Christmas lectures at the Royal Institution have been about maths this year. So we've seen lots of cool maths communicators doing maths on TV.
For those of us who are not in the UK, could you tell us a little bit about what the Christmas lectures are?
So the Royal Institution is one of the UK's sort of major scientific, I guess, learned bodies. Like they've got a big old building in London, which I think is the main criteria. And they have since historical times, they've done lectures at the Royal Institution. So people like Michael Faraday and like the very early sort of scientific pioneers of that kind of thing at the Royal Institution would do public lectures and people would come and watch them. And I think since something like the 1960s or 70s, they've been putting them out on television. So at Christmas, they get a person to come and do 3 lectures and they film them in December and then they put them out from sort of Boxing Day onwards as sort of 3 1-hour TV specials. And they're really cool. Like they could be on any topic within science. They could be like a biologist or a chemist or whatever. And they do loads of like demos and experiments on stage and they get volunteers from the audience to come and join in with everything. And I think there's been maybe 3 or 4 times in the history of the whole thing that they've actually been specifically done by a mathematician. So the first maths one was 78, I think was Christopher Zeeman. And since then we've also had some from Marcus de Sautoy and we've had Professor Ian Stewart. I don't know why he's the only person who gets a title, but anyway, this year it's been Dr. Hannah Fry, who is amazing and does loads of cool TV stuff with maths and works at UCL as a researcher in maths. And she was sort of half helped out by maths communication stalwart Matt Parker, who you may have heard of off the internet, I guess. Some people have heard of him. And he was also kind of involved and did loads of sort of cutaways and demos and extra bits of presenting around the lectures. But it was mainly Hannah Fry bringing in loads of people to tell us all about different bits of maths and show off lots of cool things.
So what were some of the topics that Hannah Fry and Matt, friend of the show, Matt Parker, talked about in these lectures?
The overall topic is they're called Secrets and Lies. So it's about kind of the way that maths, is part of the world around us and does various different things. So the first one is kind of probability and how complicated systems work and probability type stuff. And then the second lecture was kind of algorithms and things like that. And then the third one is about problems and limitations of maths and fake news and statistics and that kind of stuff. I can't remember which one it was in, but one of them, they've had a machine which was 80% accurate at telling you what your Christmas present was going to be. And it was a really nice demonstration of how you can have false positives when you have something that's not 100% accurate. And, it's like it's unexpected how often it will give you a result that's inaccurate. Even if you know what the accuracy is, it's that kind of paradox that people get confused by a lot. And they've done lots of big explosions and lasers and brought in lots of exciting, demos and things. And I think they've really kind of made maths look cool across the whole thing.
That's great. I look forward to figuring out a way to be able to watch those in the United States.
Well, I think they're going to put them out on YouTube. So the Royal Institution has a YouTube channel. So they're going out, I think it's across 3 days. So maybe the last one's tonight. And then the BBC like online streaming platform iPlayer for like a month. And once they come off iPlayer, they go straight onto YouTube. So I think by the end of January, you should be able to watch them.
Oh, excellent. That's great. So, well, I do love a good mathematics communications story, and more people talking about math in public, I am totally happy about. I guess we should probably talk a little bit about some more directly mathematical things. And one that really struck me this year is that we have finally had a woman win the Abel Prize, which this year went to Karen Uhlenbeck for And this is from the prize announcement: pioneering achievements in geometric partial differential equations, gauge theory, and integrable systems, and for the fundamental impact of her work on analysis, geometry, and mathematical physics. Now, I will admit to not really knowing much of the mathematics itself, but from all of the write ups and everything, it seems that Karen Uhlenbeck's work is absolutely just groundbreaking and that this is an incredibly deserved prize.
Yeah, and I think I equally don't necessarily know exactly the maths involved here, but it does sound like she's done some really, really good work. And I guess so, like the Fields Medal for the first time was given to a woman in 2014 for Mariam Mirzakhani, and that was a major step. And this is the first Abel Prize for a woman as well. Also, as well as being a woman, she's also a mathematician, and that's probably the more important thing here, that she's done this amazing stuff. So there's loads of stuff on the Abel Prize website that has kind of lay summaries and that kind of thing about the work that she's done. But it is very cool. And by all accounts, I think has she also done some kind of like she's donated some funding to research, I think.
Yeah, so the Abel Prize comes with a rather healthy purse, and Professor Uhlenbeck has decided to use some of that money as a donation to Edge, which I have talked with the people who founded and run Edge on this program before. It's enhancing diversity in graduate education, and they're establishing the Karen Edge Fellowship Program, which will support and enhance research programs and collaborations of mid-career mathematicians who are U.S. citizens and members of minority group that is underrepresented in the field of mathematics. And so Edge has done a great amount of work for trying to diversify and spread inclusion within mathematics for early career mathematicians. So this is going to start helping some mid-career mathematicians as well, and will provide also for visits to the Institute for Advanced Study in Princeton, which is one of the places where Karen Uhlenbeck holds a position.
Yeah, and I guess like a major hub for maths, so a good place to go. Yeah. That's excellent. I've just quickly Googled how much the actual prize is, and it's like over $500,000. Like it's a huge amount of money. So she's obviously massively deserving of that. But the fact that she's chosen to do this with it is very cool.
So 2019 was also the second year of the A periodical awarding the prize, the most interesting mathematician in the world. So I was wondering if perhaps I could hear a little bit about how the second round of the Great Internet Math Off went.
Okay. Yeah, this year I had to run it again because people assumed it would. So I got another 16 mathematicians. Did I have 16 last year?
I think so.
Probably.
Yeah.
Yeah. But I changed the format a bit this year so that everybody got more chances to show off, basically. So there was a group round where everybody got 3 goes, and then semi-finals and finals. So we got in total 50-odd bits of maths out of people. It was really good. I had a lot of fun doing it. We got some really good things. And again, from my point of view, I got to know a lot more mathematicians around the world that I hadn't really known anything about beforehand. And eventually the winner was one of those people I didn't know beforehand, Sophie Carr. I very nearly said Sophie Bayes because that's her Twitter name, isn't it? In my head, she's Sophie Bayes. Yeah, she did some lovely videos, mainly about stats and Bayes' theorem, a really personal one about what got her into maths and stats. And then in the final, a video about Bayes' theorem. There were some Lego people involved. Yeah, so it all went well again, which I think means there has to be another one.
Well, potentially, yeah.
Oh, there we go. Some breaking news here that we have another Great Internet Math Off.
Yeah, so next year I feel like I should change the format up again. We always have this tension between it being a competition, so that there's some reason to follow along with it, and wanting to get the maths out. So try and fix the format so that people do more maths things. Because nobody really wants to be in a competition. It's not a real title, world's most interesting mathematician.
It's not?
So it's definitely
There's
not.
a
I just made it up. I
There's a
think maybe
teacup and everything.
Yeah. So next year we'll have to do some thinking about what can be done. I'm quite keen on the team structure, but then that seems to put some people off.
Maybe just a full ladder tournament. Just put everyone in and then get everyone to, pitch things against each other and use it as a ladder. I don't know.
How long will this take?
So 2019 also turned out to be, oddly enough, a very important year for multiplication, which struck me as, it's sort of weird. Like, it seems like 2019, we should have already figured out multiplication pretty well, right?
You would think, yeah.
But instead, we ended up with a new algorithm for more quickly multiplying numbers together, which was worked out by a mathematician at the French National Center for Scientific Research, Joris van der Hoven, and David Harvey from the University of New South Wales were at least two of the co-authors on this, and they found a algorithm that can multiply numbers together in log n time, which is faster than the old in log n log n time.
Ah, of course.
And
Yeah, so I guess this is about if you're going to multiply two numbers together, you've got the sort of classic method where you put the two numbers above each other and you do one of the columns, and then you write the stuff at the bottom, and then you put a 0 and you move across and you do the next column, and then you add together the things. And I guess it'll there'll be a certain number
and that actually has n squared times, which means it's really slow.
Right.
And then in the 1970s, Anatoly Karatsuba actually proposed a more efficient way, which got it down to more less. It was 2n times, and then people have been working on it since.
Yeah, it's in terms of how many actual calculations you have to do involved in this, because some of it's just moving numbers around or copying them from one place to another. But if it's actual kind of number crunching, steps that you have to do, you can get that more efficient. I mean, to be honest, I'm still just going to do it that way because that's the way I do it if I'm writing down on paper. But I imagine you can implement these algorithms in computers or whatever.
Yeah, as far as I can tell, these are definitely not for how we should be multiplying things.
Right.
That it's definitely for how computers will be multiplying things. And other multiplication news, one of the big results, which is the knocking down of the last two numbers less than 100 to be written as the sum of three cubes.
Oh my God, massive news. Yeah. Yeah, this was a real the kind of news story that mathematicians were like, wow, a thing has happened, and everyone else is like, has it? Yeah, I guess. But yeah, this is the idea that if you have a number, can it be written as a sum of three cubes? And for all the numbers for up to a certain amount, we know what the answer was, except for 33 and 42. And they've both been knocked down this year. We've discovered, so in March, they found that 33 could be written as a sum of three cubes. And in September, we discovered that 42 could be written as a sum of three cubes, which is, it sounds simple, but the three cubes involved for 42, one of them is, hang on, I'm just counting how many digits it is. 12, 16 digits long, and it's a negative number that starts with an 8 and is 16 digits long. And then the second one is similarly a number that's about 16 digits long and starts with an 8, and then the other one is even longer. So it is technically a sum of three cubes, but it's like a massive negative one and a massive positive one, and it it comes out to total 42 overall, but it's not the kind of thing you would immediately look at and go, oh yes, of course that equals 42.
Well, and so now we finally know the question to which the answer is 42, which is, what are these massive numbers cubed and summed together equal?
Well, exactly. It's one of many questions to which the answer is 42. Yeah, but I think in general they've got. I'm just having a look at the aperiodical post that we did about this because it was big news, of course. So numbers of the form 9k plus 4 or 9k plus 5 can't be written as a sum of three cubes. And we were pretty sure, so there's a conjecture from 1992, that every other number could be written as a sum of three cubes, and 42 hadn't yet been found like a way to do that. But people obviously continue to work on these kinds of things just to check. But yeah, I guess this will have again just been crunching a load of numbers and cases through a computer. But there's a number file video that covers the 33 case that explains some of the stuff around it as well.
And in other calculation news, people are apparently still figuring out more digits of pi. This is one that really really kind of sets me on edge. People who have listened to other work than Relatively Prime that I have done will know this about me already, but I don't necessarily see why this is one of the few news stories that ever gets into the New York Times, that we somehow now know more trillions of digits of pi, but we now know it up to 31 trillion digits.
Well, specifically 31.4 trillion.
Oh,
So
I'm
actually
sorry.
10 pi trillion digits. They've deliberately done such that the number is a multiple of a power of 10 times pi, um, I guess, which is kind of fun. I think I have an idea as to why this kind of thing ends up in the news rather than your stories about other things. And I think it's just because this is a thing that you can explain. Like if you say to someone, have you heard of pi? Yes. Oh, it's got lots of digits, hasn't it? Yes. Well, now we know this many of them, and they're like, oh, that's a thing, and I understand what you mean. Whereas if you say, we've proved this obscure result in graph theory or whatever, you can't really do a thing in the New York Times about that in quite the same way. So I guess this kind of thing gets a bit more attention. When in practice, if you're actually in maths, you kind of realize that this is essentially just stamp collecting. This is just, oh, we've done a thing, great. And it's nice that we've got computers that are advanced and we've got algorithms that can do these calculations more efficiently. Just like the multiplication thing, like, you're not just sat there drawing a big circle and measuring the diameter and the circumference and dividing one by the other. Like, there are really nice algorithms that people have come up with. So in this case, they use Chudnovsky's algorithm, which is apparently O of n log n cubed. So they found a reasonably efficient way to actually calculate these, and they put it through the computer. And this apparently has been running on a cloud computer using 2,795 machine days or 7.6 machine years to work this out, which is pretty decent amount of work to put into something. But the mathematician Emma Haruka Iwao announced the result, and the previous record was I seem to remember when we knew 10 trillion digits, but the previous record was 22 trillion digits, and now we know 10 pi trillion digits, I guess. So we're working our way up. Not that that's actually a goal of getting anywhere. Like, we're never going to finish. We're not going to get all the digits of pi.
Oh, could you
But
imagine if
it's,
we did? Like, all of a sudden we just realized that pi's like
yeah.
non-transcendental, like it just stops. It's
Like, yeah, you just, like, a mathematician's just sat there and they do some working out and then they look up and they go, oh, it's just ends with a 7. Who knew? Like, that's interesting. That kind of breaks a lot of things. But yeah, no, we're not going to do that. But I think it's partly about this idea of trying to build more and more powerful machines and more efficient algorithms to do this kind of thing. Because obviously, the more breakthroughs we make in that area, the more useful those will be in like applied mathematical things where we need to actually do these big calculations. But I think also it's just a thing that everyone can latch onto and be happy about, that we're making progress on a thing.
So this calculating pi is linked to the thing about the new algorithm for multiplication. Calculating digits of pi really it's a computer science problem now. It's all about writing algorithms and using computers to do it. And this effort was, I think, an advert for Google's cloud computing service. It's right that nobody needs this many digits of pi. I mean, it's just an absurdly large number. But what's really an absurdly large number is the number of digits at which this new multiplication algorithm starts being better than the previous one. I don't know what it is, but I can remember reading it a while ago. It's a number so enormous that you couldn't even write it down, or you couldn't even store it on a computer that you've got now. It's a ridiculously large number. The way you talk about how efficient an algorithm is, this big O notation, it's some constant times a function of n, and was it Chudnovsky algorithm for pi? That was like n log n cubed or something, and then that'll be times 12 squillion something. So at some point it becomes worth using this algorithm. For these multiplication algorithms, the straightforward one is actually decent for pretty big numbers. You have to get onto absurdly big numbers that you'd never encounter in the wild before even the Karatsuba algorithm is worth doing. So again, that's another sort of pointless quest to find the best multiplication algorithm, or a dead alley. There might be one that's even faster and works better for small numbers, but it doesn't leap out to you as obviously pointless as computing digits of pi.
No, that's actually a really good point. I hadn't really thought about it that way, but it seems like we've made that we've done such good general algorithm design up to this point that it is becoming harder and harder to find the sorts of problems to actually even look at and think about solving.
Well, there are still plenty of problems that don't have efficient algorithms, and for which there could be efficient algorithms that work on the sizes of problems that we actually deal with, like pretty much anything in NP. But these ones where they're really being looked into a lot, maths is full of these sort of intermediate results that are a little bit there, but you can sort of see that they're not the big insight that's going to really get you a long way. So they're sort of dead ends in a way, or they're just, oh, well, this method didn't quite work, we'll try another one.
To move from problems where we're making a bunch of headway, but maybe it doesn't matter, to problems where we're making some headway, but it definitely does matter. One other thing about 2019 that I noticed is it seems to be the year of making some steps forward on what are considered the most important unsolved mathematics problems. And 2019 saw movement on both the Riemann hypothesis as well as the Collatz conjecture.
So the Collatz conjecture progress has been Terry Tao, and he's proved result. The title of his post was "Almost all Collatz orbits attain almost bounded values," which is an incredibly mathematician way of putting this. I mean, almost is carrying a lot of weight in that sentence, basically.
Yeah, that maybe that may be one of my favorite mathematical sentences ever.
It's like saying some stuff may happen. So it's in particular not proved for all cases, but Collatz orbits, I guess. So the Collatz conjecture is about this particular pattern of functions. So there's a function where you start with a whole number. If the number is even, you halve it. And if the number is odd, you triple it and add one. And this kind of gives you a little kind of toy machine that you can push numbers through, and it will always give you out a whole number because you're only going to halve it if it's even, in which case you still get a whole number. And if it's odd, you triple it and add one. And what's interesting about this particular set of rules, because obviously you could pick any set of rules. You could say even numbers do this, odd numbers do this. So you could say numbers that are a multiple of 3, or one more than a multiple of 3, or one less than a multiple of 3. Like you could basically design any system like this that you wanted. But this one in particular seems interesting because it's conjectured that all numbers under this particular set of rules will do the same thing. So you could, for instance, have a system where some numbers go and kind of converge towards one particular value, other numbers go somewhere else, other numbers go off into a loop and just keep looping around the same set of numbers. But in the case of the Collatz conjecture, everything goes back to 1. And of course, when you reach 1, if you want to continue, you can triple it and add 1. So you go to 4, then you go to 2, then you go back to 1. So you're kind of trapped in this sort of tiny little loop at 1. And Collatz orbits, I guess, are the paths that these numbers take. So you've got this machine, and it gives you this system where you can think of the things as being moving around in an orbit. And the title, again, in case you've already forgotten because it was so memorable, almost all Collatz orbits attain almost bounded values. So, you've got these little orbits, and the proof essentially is to do with how those all behave, because obviously you can't just check infinitely many things. You need some kind of general results about this, and this is sort of a general result that is potentially something that may have counterexamples, but they might be incredibly rare and quite difficult to find.
And it's so great to see big movement on a problem that has really been around for quite a while now and has really intrigued and fascinated mathematicians for pretty much since it was first stated.
Yeah, and it's a lovely little problem because it's so simple to state. Like you could give this to a 7-year-old and say, what happens to this number if you put it through this thing? Like they could answer that question, and if you give them a calculator, they could probably go on quite a way. But it kind of behaves in slightly odd ways. So like if you start from any reasonable number like 10 or 12 or whatever, you kind of move around a little bit, but you very quickly end up back at 1. If you start with, I think, 27, it takes like over 300 steps and it goes via 9,232 before it gets down to 1. But this conjecture is still open. So essentially we could find at some point potentially a number that doesn't go to 1, but no one has found that yet. So it's still an open problem, and it could be disproved by finding that, or it could be proved by someone extending this result that Tao has put out and kind of using it to pin down all the gaps.
to move from problems that are easy to state to problems that I have never successfully fully understood, the
Yep.
Riemann hypothesis has had some movement as well. Specifically, Griffin, Ono, Rowland, and Zager used Jensen polynomials, which are something that was originally designed by Johann Jensen and George Polya. And they used these Jensen polynomials to, according to the article I'm reading here from mathscholar.org, resurrect a line of reasoning long thought to be dead.
Wow.
And they resurrected it and then proved a result that can be viewed as yet another step that shows that the Riemann hypothesis is probably right, but this is still well short of offering a full proof. But it's another step along that a couple of 100-year-long path that we've been on trying to finish solving this problem.
Yeah. I guess Christian may have more to say about this. I mean, the Riemann hypothesis is it's kind of number theory, but it's kind of functions and it's kind of infinity and it's kind of prime numbers. And it ties together a huge number of different areas of maths. But it is one of those sort of big, sort of newsy stories that people are excited about because it's one of these prize problems and it's been around for such a long time. But it looks like they found something that someone proved a while ago that's equivalent to the Riemann hypothesis and then made some work on that.
Yeah, so to tie together Collatz and Riemann, with Collatz, Tao has shown that if there's a counterexample, or if the set of numbers that could be counterexamples gets smaller and smaller as you go further down the number line, so it's more likely to be a smaller number than a bigger one-ish, maybe. Or maybe there are lots of them, but they get rarer. But you still don't know where they are or how many there are. There are sequences or properties that numbers can have where there's only finitely many examples of them. There's the Munchausen numbers, which I don't know if that's a good name for things. I don't know if that's still okay. But 3435 is a Munchausen number because 3 cubed plus 4 to the 4 plus 3 cubed plus 5 to the 5 is equal to 3435. And it's a really simple proof that there can only be finitely many of those. So you know after you've checked up to a certain point, you've either found them all or there weren't any. With Collatz, you don't know how far down you have to go or if there just are infinitely many. With the Riemann hypothesis, what this new result shows, from my very quick skimming of the same press release you two are reading, is that they've shown that for sufficiently large n, effectively the Riemann hypothesis holds. So the Riemann hypothesis is equivalent to several other statements. A lot of work has been done to show other things that if they're true, then Riemann is true, and vice versa. They've shown it in terms of these polynomials and the parameterize with this n. For sufficiently large n, it holds, which means that now there's sort of a bound, and you just have to check less than that, which narrows it down a lot in a way.
That's exciting, yeah.
Yeah, it definitely is exciting, and it's I think a really good sort of insight into how mathematicians work, because a lot of times this is something even I tend to think and talk as that, like, mathematics problems tend to be not solved until they're solved. Like they're just, they're not solved, and then all of a sudden someone comes up or a group of people come up and they solve the whole thing. And I think that this is a really good example of the piecemeal sort of way that mathematics tends to actually work, where especially with these big, hard to solve problems, people will keep on chipping away over time, working to get to the point where the problems are actually finally in a small enough space that they can be solved.
Yeah, I think it's to do with the fact that when you think about maths, you think about it as being full of things that are either true or false. There's that kind of very black and white sort of aspect to it. But actually, things might be true, but they might be true for some values, or they might be true for all but finitely many values. And there are degrees to it, and a lot of the maths that's been done has been done over centuries and by a bunch of different people working at different times on the same kind of thing, and just kind of making a bit more progress with it each time. And that's one of the wonderful things about it, because it is something that you can play with, put down, and then someone else can pick it up, because it's just numbers and ideas. It's not something that's necessarily that personal to you, even if you spend years working on it. As long as you can explain it sufficiently, then anyone else can then take it and use it, which I guess is part of the beauty of it.
Well, while there was a lot more mathematics that did happen this year, I do think that this was a pretty good wrap-up of some of the things that did happen. And so I want to thank Katie Steckles and Christian Lawson-Perfect from the A Periodical for joining me on this year-end Relatively Prime wrap-up. Thanks, y'all.
Cool. Have a good New Year.
Well, thanks for having us.
And that is all the time we have for this episode of Relatively Prime. I want to thank all of you so much for listening. And I want to thank Katie Steckles and Christian Lawson-Perfect for joining me on this 2019 year-end wrap-up special of Relatively Prime. You can find their work over at aperiodical.com, which you should be checking out regularly for wonderful, insightful math news anyway. Also, I need to thank Lowercase N, whose music I am talking over right now. You can find them over at lowercasен.bandcamp.com. But most of all, truly most of all, I want to thank all of my Patreons on Patreon. Because without them, the show wouldn't exist. You can join their number by going over to patreon.com/relprime or relprime.com/support. And over on relprime.com, you can also find some show notes and links to the things that we talked about on this episode, as well as links to Lowercase N and previous episodes of this show, where you can hear all sorts of mathematical stories, which once again were made possible by the wonderful people who give me just a little bit of money to help make this show over on patreon.com. And of course, all of you who gave money for the Kickstarters for the first 2 seasons, I will never forget y'all. Y'all are the reason that Relatively Prime ever was able to start existing in the first place. It is the end of another year, end of a decade, the only decade in which Relatively Prime has been made. So I am feeling a little bit nostalgic and very, very thankful to everyone who has helped make this journey a reality. So that is just about it, other than letting you know that, as always, Relatively Prime is made with a Creative Commons Attribution Share Alike license, so please feel free to remix it, as long as you say that you got it from Relatively Prime. And then, just one last time, in this year, in this decade, have a matherific week, month, year, and decade, y'all.